If we want to calculate how big an independent foundation of a column is, first we add the axial force of the column. Because the foundation is buried in the soil, so the base also bears the weight of the soil above the base, and the weight of the foundation. These three forces will produce a uniform pressure on the base, and this pressure is equal to the sum of these three forces divided by the base area, which we record as pk. If you use a cube to represent the base pressure, the height of the cube is pk. If there is a bending moment at the bottom of the column, what about under the action of this bending moment? The foundation will rotate around the planetary axis, and it is clear that the pressure on the left edge is the largest, and the pressure on the right side is negative, and the edge pressure is equal to the bending moment divided by the cross-sectional modulus, one positive and one negative. If we still use a shape to represent it, which is what it looks like, we superimpose the two shapes, add the positive ones, and subtract the negative ones, and we get such a trapezoidal hexahedron. This is the pressure distribution at the base of the unidirectional bias column. The long side is the maximum pressure, the short side is the minimum pressure, the middle is the average pressure. Of course, there is a direction of bending moment. We use the same method to superimpose. We will get such a shape. The maximum pressure is at this corner, the minimum pressure is at this corner, and the average pressure is still in the center of the foundation. If you want the foundation to be able to withstand this column, then the average pressure cannot be greater than the bearing capacity of the foundation, and the maximum pressure cannot be greater than 1.2 times the bearing capacity of the foundation. If such conditions are met, our base size is basically reasonable.